Hello, ladies and gentlemen, especially A2 chemistry students. I hope you're struggling because if you're not, you're doing A2 chemistry the wrong way. Right. This is part two of the further aspects of equilibrium past papers. So part one is already uploaded on my channel. You can have a look at it. I'll post it somewhere here. If I haven't, just search up Science with Kasmani on YouTube, Equilibrium Part 1 past papers, and you'll find me attempting all of these. Yeah. So yeah, today is part two for equilibrium past papers. We're gonna be doing some questions like we did in part one, and let's see how many questions we end up doing by the end of this record. All right, Bismillah ar-Rahman ar-Rahim. So this question right here, the buffer solution question, is a continuation of this right here. So let's read this again. Question 11 says that I have a solution Y. This solution Y is hydrochloric acid. Now, hydrochloric acid, obviously, you guys know this. This is a strong acid. Solution Z is aqueous. What does aqueous mean? Aqueous means dissolved in water. So this is aqueous 4-chlorobutanoic acid. Again, there is no tension on if you don't know the name or if you do know the name. Again, it does not really matter because this is a name you learn in organic chemistry. 4-chlorobutanoic acid is basically a 4 carbon containing carboxylic acid, hence the word but. So this would basically be C3H7COOH. But this is butanoic acid. This is 4-chlorobutanoic acid, meaning there is a chlorine atom on the fourth carbon atom of this carboxylic acid. So basically, when you draw out the entire carboxylic acid, which consists of 4 carbon atoms, on the fourth carbon atom, you're going to have a chlorine atom attached to it. That's 4-chlorobutanoic acid, this right here. Now, it says the pKa of this weak acid. How do I know it's a weak acid? Because, let me write this down here. All organic acids are weak acids. All organic acids are weak acids. Now, some students might ask me, sir, how do you know this is an organic acid? It's because organic acids are carbon containing acids. Look at this, HCl. Does this contain carbon? No. This is not an organic acid. This is a normal acid and this is strong. But because look at this, it contains 3 carbon atoms, or in fact 4 carbon atoms. It's a carbon containing acid. And carbon containing acids are called organic acids. And are they weak or strong? They are weak acids. So this is why you have the Ka or the pKa value, because always remember the examiner is only going to give you the Ka or pKa value of an acid which is going to be weak. A Ka value for a strong acid does not exist. Ka or pKa values for weak acids only exist. This equilibrium constant is made for these types of acids. So it says it's 4.52, the pH of both solutions is 4, blah, blah, blah. Okay. Write an expression for Ka, we did this. Write an expression for pKa and Ka relationship, we did this. Calculate hydrogen ion concentration in both solutions, we did this. Calculate the ratio. What ratio? Ratio of HCl concentration in Y divided by this weak acid concentration in Z. And we found that out too. If you want to have another look at it, if you don't understand it by what's written here, just go to part one of this video and you'll get it of this chapter past papers and you'll get it. Okay. Now let's go to part B. Part B says that I have a buffer solution. Interesting. Buffer solution questions are always interesting. You have a buffer solution, and the buffer solution is of pH 5. Okay. As soon as you see the word pH, always know that it's gonna ask you in some or the other way the conversion between pH to protons or H plus ions. And you should know this. What's the conversion? pH is equal to minus log concentration of H plus ions. If you have the concentration of the protons, you're going to get the pH. If you have the pH, you're going to get this. It's a relationship expressed by this formula, which you should remember. So if the question is giving you the pH, in some or the other way, it's going to ask you to calculate this. If it's giving you this, in some or the other way, it's going to ask you to calculate the other part. Okay, so you have a buffer solution of pH 5. Okay, is this an acidic buffer or a basic buffer? This is an acidic buffer because Acids are those substances or those compounds which have a pH of less than 7. So this is an acidic buffer. And remember, just like in the last class we talked about, what is an acidic buffer made of? An acidic buffer is made of two things. It is a mixture of the weak acid and the salt of the weak acid. Just these two things make up an acidic buffer. Okay. So this is produced and it's also telling us some details about this buffer. How is it made? It's made by adding sodium propanoate to 5 grams of, look at this, propanoic acid. Is propanoic acid a carbon containing acid? You would say yes. The formula for propanoic acid would be C2H5COOH. It has carbon atoms. Therefore, it is a carbon containing acid. And what is another name for carbon containing acids? Organic acids. And then, are organic acids strong or weak? Organic acids are weak acids. So, meaning propanoic acid is a weak acid. Okay. So, this buffer solution of pH 5 is made by adding sodium propanoate and how much? To 5 grams of propanoic acid in 100 cubic centimeters of distilled water. Okay. Calculate the mass of sodium propanoate that must be used to produce this buffer solution. The Ka of propanoic acid is this, the Mr is this, and the Mr for the salt of the carboxylic acid is this. Okay. This is a bit complex to understand because it has many steps. Let's see. Now, always, chemistry is the only subject in A level sciences wherein you don't need to have a roadmap to answer the question. So, for example, in physics, you do need to know, right? For example, uh, what step do you need to do to get to the final answer? So, let's say you have to find the air resistance first, then you have to find the resultant force, then you have to find the mass and the acceleration, and then eventually you will get to the final answer. Similarly, in biology, you need to write about antibiotic resistance. Then, how was antibiotic resistance produced? And where is it produced? How is it produced? And then you get to the answer. In chemistry, you don't need to have some sorts of roadmaps. Just start with the question and see where you end. So, always start with that part of the question which is given to you. What is given to us? They have given us some details on how did they make the buffer solution. One. And two, they gave us the Ka value. So first, let's start with our usual steps. Let's start with making the buffer solution. How do you make a buffer solution? You write down the dissociation of the weak acid and then the dissociation of the salt of the weak acid. So let's write down the dissociation of the weak acid first. So you have propanoic acid, that's C2H5COOH. Now, how does propanoic acid dissociate? Fully or partially? Most of you guys would say partially. Why? Because it's a weak acid. Weak acids are called weak acids. That's why their name is there because they partially dissociate. They do not fully dissociate. For example, if you take a container and if you put 100 propanoic acid molecules, two, three, or four, max four, are gonna dissociate. 96 are gonna remain undisassociated. So shouldn't I add just a reversible arrow here instead of a complete forward arrow? Because this would indicate that every single molecule of propanoic acid has dissociated, isn't it? So this is why I use a reversible arrow. So C2H5COOH reversible arrow, C2H5COO minus plus H plus. If you're confused on how did I disassociate this into this and this, always remember, whenever you disassociate an acid, you disassociate it in such a way that one of the ions is a proton, an H plus ion, and the other one is the negative part of that ion. Let's take another example. Let's say I have ethanoic acid. So when you disassociate, there are going to be two ions. The positive part of that ion and then the negative part of the entire container. So this is going to be H plus, and what's the remaining part? CH3COO minus. And this exact process is not only limited to organic acid, it also works in inorganic acids, let's say HCl. Now, HCl is a strong acid, right? So I'm going to use a complete forward arrow and not a reversible sign. Okay, my hair is, I'm having a bad hair day, sorry. Okay. Now, HCl dissociates into, again, the positive part, the H plus ion, and then the negative part, the Cl minus ion. So we have H plus Cl minus. Let's take another example. Let's take H2SO4. Again, dissociates into the positive part, the H plus ion. So 2H plus, and then the negative part, the sulfate ion. So SO4, 2 minus. Now, why did I write a 2 here? Because there are two hydrogens, right? And why did I write a 1 here? Because there's only one sulfate ion. So let's go back to our question. Propanoic acid dissociation. So C2H5 COOH. How does this dissociate? Into C2H5 COO minus plus H plus. Okay, now we have already dissociated the weak acid. Let's try to now ionize or dissociate the salt of the weak acid. What's the salt? Sodium propanoate. How do we write down sodium propanoate? The only difference is instead of the H, just write down the metal. So in this case, Na. Everything else remains the same. So C2H5 COO Na. Simple. Okay, let me ask you guys this. Are all sodium salts water soluble? Meaning, are all of the salts that contain the sodium ion soluble? So let's say NaCl. Is NaCl soluble? That's a compound which contains sodium. Is it soluble? Yes, it is soluble. Okay, what about NaBr? Another compound which contains sodium. Is this soluble? Yes, it is. What about NaF? Yes, another compound which contains sodium is also soluble. Similarly, this is a compound that contains sodium, and that's why this is called a sodium salt. So all sodium salts are water soluble. You might have learned this in IGCSEs too. So let me write this here. All sodium salts are water soluble. Now, what does that mean? It means that if you put 10 molecules of sodium propanoate into a container containing water, all 10 of those molecules are gonna fully disassociate. It's not gonna be partial like the weak acid. It's gonna be full because it is fully water soluble. It's not partially water soluble. So I'm gonna put a full forward arrow here, and this is gonna be C2H5 COO minus plus. Now, is there an H plus? No. Instead of an H plus, is an Na plus right here, like this. This is our acidic buffer. Okay. Now let's write down the other thing which we were given, the Ka. We're given the value of Ka. Can we write down the expression for Ka? Yes, we can. So the Ka expression, again, what just like we talked about in the last class, how do we write down the expression of Ka? In the same way in which we write down the expression of Kc. Ka is an equilibrium constant which is used to write down the dissociation for weak acids, right? This A refers to acid dissociation. So basically, or just remember this bottom line that Ka is a constant which is used whenever weak acids are dissociated. So we are gonna make our Ka expression according to this and not this. So again, how do you write Ka? In the same way in which we write Kc, products divided by reactants. So these are our two products, and this is our only reactant. So this is the concentration of C2H5 COO minus times the concentration of H plus divided by the concentration of C2H5 COOH. Okay, now let's actually look at what was the question because I forgot the question between all of the stuff. Let's see. The question was calculate the mass of sodium propanoate that must be used to produce the buffer solution. Okay, so we need to calculate the mass for this. If I know the moles for this somehow, if I know the moles for this compound, can I calculate the mass? You would say yes, because moles equals mass upon molar mass. If you have the moles, you already have the molar mass, just multiply them together and then you get the mass. So what should our first step be? Our first step should be, or in fact, our last step should be get the moles for sodium propanoid. Now let's work our way backwards. Okay, we need the moles for sodium propanoid to solve this question. How do we get the moles for sodium propanoid? Let's see. How about taking the concentration and the volume and then finding out the moles? So remember this formula, N equals CV. If you have the concentration of this at equilibrium and you have the volume at equilibrium, you can get the moles, right? So in order to find the moles of sodium propanoid, we are gonna have to find the concentration of sodium propanoid. Okay, we're getting somewhere. Let's see. Propanoid. Okay, my spelling is absolutely insane. It's sodium propanoid. Okay, never mind. Now, you need the concentration for this. Now, tell me this. Is this a reversible reaction or an irreversible reaction? This is an irreversible reaction, meaning if 10 molecules dissociate, you get 10 molecules here and 10 molecules here. If 1,000 molecules dissociate of sodium propanoid, you get 1,000 here and you get 1,000 here. So, do you see a pattern? The number of molecules of this ion are equal to the number of molecules of this ion, meaning the number of moles of this ion is equal to the number of moles of this. So if you have to find the moles for sodium propanoid, which is this one, let's just find the moles for this, right? So let's change up our working or our, uh, what do you call this? Let's change our route a bit, right? So now we're not going to be finding the concentration for this. We're just going to be finding the moles for this. And then we're going to use something called stoichiometric ratio. This is IGCSE stuff. If this is 1 mole, this is 1 mole. This is 2 mole, this is 2 mole. If you get the moles for this, let's say 500, then this is also 500 moles because this is a 1:1 ratio. And this is a irreversible reaction. What if it was reversible? Could we have used the stoichiometric ratio? If you're using it, you're wrong. Why? Because the only reason we can use stoichiometric ratio is because we are 100% sure the number of molecules you put here equals the number of molecules here. How are we so sure? Because every single one of those molecules disassociated. Now compare that concept to this. If you put 100 here, are you gonna get 100 here? No, because this is a reversible reaction. Remember, we said that this partially disassociates. So if you put 100 here, you're not gonna get 100 here. So does this stoichiometric ratio work? It does not work. So always remember, stoichiometric ratio only works in irreversible reactions. Now, again, I know it might seem as if it's too many concepts jumbled up at once, and it's because it's a mixture of many different topics. This is stoichiometric ratio, molar ratio, concentration, Ka, equilibrium, all at once. So you need to understand each concept first, and then have the ability to link it together. So it only works in irreversible reactions. Okay. So what's our route now? So to find the moles for sodium propanoid, just find the moles for this thing, C2H5 COO minus. Okay, now we have the Ka value. We have the concentration of H plus ions. Now you might look at this question and say, where do we have the concentration of protons? Well, we do. Look at this, we have the pH. If you have the pH, again, as I was saying, if you have the pH, you have the H plus ions already. So you have this, you have this. Now, in order to find the concentration of this, you need to have the concentration of this. Now, let me ask you this again. If you put 100 molecules here, how many do you think are going to dissociate? As we talked about, 3 or 4 max. So 96 molecules would be there in this container at equilibrium. You put 100, only 4 dissociate, and at equilibrium, you still have 96. Was this change substantial? As in, was this change in the number of molecules which disassociated, was this change big enough that you can record it? No, right? It's just 4 out of 100. That's like 4% of total molecules. This is not big of a change at all. This is called a negligible change in concentration. And always remember this. In the dissociation of weak acids, which is what we just did right now, in the dissociation of weak acids, W dot A, weak acids, the concentration of the weak acid before and at equilibrium remains the same. Before equilibrium was established, you had 100 molecules. After equilibrium was established, you have 96 molecules. It's more or less the same thing. It's a negligible change in concentration. You don't take into account of the change in concentration. So the concentration before and at equilibrium remains the same. So here, I agree. This is an equilibrium constant. So shouldn't we use the concentrations at equilibrium? Yes, but remember what we just talked about 2 seconds ago? The concentration of this at equilibrium is going to be the concentration of this at the very beginning. So let's see if we are given this concentration. We're given the mass and we're given the volume. Okay, interesting. Let's see. So to get the concentration, you use this formula, right? N equals CV, makes C the subject, so C becomes equal to N divided by V. Now we have the volume, but do we have the number of moles of propanoic acid? We don't. But we can use a formula to calculate the number of moles of propanoic acid, which is mass upon molar mass. We have the mass, which is 5 grams. We have the molar mass, which is 74. So this is just basically 5 over 74. Why are we doing this? To get the moles of propanoic acid. 5 over 74 is 0.067, or let's say 0.068 moles. Now you put 0.068 here, and then you divide this with what is the volume? 100 cubic centimeter. Always remember to convert this into decimeter cube. So centimeter to decimeter cube becomes divide by 1000. So this is just 100 over 1000, which is 0.1. So concentration here, just divide this by 0.1. This becomes 0.68 mole per cubic decimeter. You have this value right here, 0.68. Let me just draw up a new paper. Okay. So Ka, let me just copy the one we wrote above, equals concentration of H plus ions times concentration of that ion, which is C2H5COO minus, divided by the concentration of C2H5COOH. Now we have this value right here. And what's this? 0.68. We have Ka also right here. 1.35 times 10 power minus 5. So 1.35 times 10 power minus 5 multiplied by 0.68 is equal to concentration of H plus ions multiplied by concentration of the carboxylate ion. Now, what do you do? What did I just do right now? I just multiplied these two things together. Do you have this? Yes, we do. We have the pH. What's the pH? The pH is 5. You should know this by now. To just do this on your fingertips, pH equals 5. pH equals minus log concentration of H plus ions. So if you need to find the concentration of H plus ions, all you have to do is get the anti-log of minus 5. If you're confused on how did I get anti-log of minus 5, step number 1, take the negative sign to the other side. So this becomes minus pH equals log H plus. Take the log to the other side. Log to the other side switches to anti-log. So this is anti-log minus 5. And let's look at what this is. Antilog of minus 5 is just 1 times 10 power minus 5 mole per dm cube. So you have this as well. Let's just divide both sides by concentration of H plus ions. So 1.35 times 10 power minus 5 times 0.68 divide by 1 times 10 power minus 5. What do we get? We get the concentration of the propanoate ion. What's the concentration? Let's just quickly check. So we have 1.35 times 10 power minus 5 times 0.68 divided by 1 times 10 power minus 5. We get 0.918 mole per cubic decimeter as the concentration for this. Now, you have the concentration of this ion. If you have the concentration for this, can you convert this into moles? Yes, we can, because if you remember, we talked about stoichiometric ratio. This stoichiometric ratio only works if you're using moles. You can't really do this for concentration. So we need to convert the concentration into moles first. So this becomes N equals CV. So N equals 0.918. And what's the volume? 0.1 decimeter cube. So let's see, times 0.1, this becomes 0.0918 moles. Now remember, stoichiometric ratio. If this is 0.0918 moles, this is 0.0918 moles. We got to this step. We now have the moles for sodium propanoate, which is 0.0918 moles. Now, if they're asking you for the mass, just use this formula. N equals mass upon molar mass. Take the molar mass of propanoic sodium propanoate and multiply it with the moles. That is 96. Just a second. I think I messed up. I think. hmm, no, I didn't. Okay. I thought for calculating the moles of propanoic acid, I took 96, but no, I took 74. So that's good. Okay. So what do we have to do now? 0.0918 multiplied by 96. That is 8.8128 grams. So this is 8.8 grams. Let's see if our answer is correct. Okay, okay, okay. What part is this? I'm not even sure. 2B, okay, 2B. So this is B, yeah, 8.76. If you round this to 2SF, this becomes 8.8 grams. Again, if you have any questions, just rewind the entire video and check for any, you know, when students just go through the entire thing in 2x, I am speaking in 2x. When you put the video in 2x, it goes to 4x. So it's going to be a bit tough for you if you're looking at this in faster speed than normal. So yeah. Again, I'm only going fast because this is topicals. When you go to yearly past papers, I'm gonna go slow and steady like a turtle. Really, really slow. Because that's yearly past papers. Topicals should be really, really fast. Okay. Now let's see. Let me erase. Let's just keep it as it is. Okay. Some dilute sulfuric acid. Okay. Some dilute sulfuric acid is mixed with a small sample of the buffer solution described in part B. So this buffer solution right here, you take a small sample of this buffer solution and you mix it with some dilute sulfuric acid. The final pH is close to 1. Explain this observation. Now, try to remember the definition of a buffer solution. What was a buffer solution? A buffer solution is a solution that resists the changes in pH when small amounts of acid or alkali are added to it. So let's say I have a buffer solution right here. If I add a small amount of an acid, this buffer solution is going to be like, no, I'm not going to let you change my pH. It is going to resist the change in pH. Similarly, if I add a small amount of base, again, the buffer solution is going to resist the change in pH. But How does it actually resist the change in pH? The thing is, if you're adding an acid, what are you adding actually? If you're adding an acid, what you're adding is H plus ions. What a buffer solution does, as in this, what I'm explaining right now, is how does a buffer solution work? If you add a small amount of acid, as in if you add some H plus ions, the buffer solution is gonna react these external H plus ions with the basic part of the solution. Now, this solution has two parts, the acidic part and the basic part. What is the basic part? This ion right here. Because remember, it can always react with the H plus ions to go backwards. Meaning it's a base, right? What is a base? Anything that can accept H plus ions. Isn't this accepting the H plus ions in the backward reaction? It is. So, and look at this. This is donating the H plus ions in the forward reaction. So this is the acidic part. This is the basic part. If you add a small amount of acid, the buffer solution is going to react this with the basic part. So what's going to happen? It's going to neutralize this. If it neutralizes the H plus ions, do the H plus ions have any effect on the buffer solution's pH? No, because they are not there. You neutralize them. You killed all of those excess H plus ions. And now let's see, if you add excess of OH minus ions, meaning if you add a base, what's going to happen? The buffer solution is going to do the opposite thing because it's opposing the change. It's going to react it with the acidic part of the solution. So what's this going to do? It's going to neutralize this. If it neutralizes this, this no longer has an effect on the pH of the buffer solution. So you could think of the buffer solution as like a kingdom, right? What does a kingdom do? A kingdom has its armies and their soldiers situated outside of the kingdom, right? Outside of the castle. As soon as an enemy comes, they shoot that enemy. They just destroy that enemy. They destroy the entire forces of the opposition. This is what a buffer solution does. You put in excess H plus ions, it's going to react it with the basic part of the buffer. You put in excess OH minus ions, it's going to react with the acidic part of the buffer. So the main purpose is just neutralizing whatever you put into the buffer, either with the help of the acidic part or the basic part. And what does the buffer solution get as a result when it does this? It's able to resist the change in pH. If the pH was 5 before adding the acid or base, whatever, it's gonna be close to 5 at the end. But now let's read this question. You have some acid which you added to the buffer solution. And now look at this. The final pH of the mixture is close to 1. First it was 5, now it's 1. This is a big change. What does that mean? It means that the buffer solution, was it successful in resisting the change in pH? No, it wasn't successful. It was not able to oppose or resist the pH change. The pH change did take place. It's asking us to explain why did this happen. Now see, you got to understand this. The reason why the buffer solution was able to maintain its pH is because any excess of H plus ions or protons that were coming in, it was destroying them, right? Because so that the protons which you're putting into the solution externally, they no longer have an effect on the pH of the solution. However, what if I told you that now which the ions you're adding into the buffer solution, they now have an effect on the pH? You would say how? Well, they can have an effect if they are not destroyed by the buffer solution, right? So let's take an example. And this will help clear things a bit. Let's say I have this buffer solution. In this buffer solution, I have 4 carboxylate ions. Let me just copy paste this. This is 1, this is 2, 3, 4, 5. So 1. Okay, let me just 1 second. So 2, then 3, then 4, then 5. Okay. I have 5 carboxylate ions. Are these ions acidic or basic? They are basic, right? Acidic are those which have an H plus ion which they can lose, which they can donate. This doesn't have one. All it's going to do is accept an H plus ion right here. So those which accept an H plus ion, they're a base. Okay. So let me write this here. This is the basic part of the buffer solution. Now, if I add externally 5H plus ions, so let's say I add an H plus ion here, an H plus ion here, 3, 4, and 5. What's going to happen? Every single carboxylate ion is going to react with one H plus ion. So this reacts with this reacts with this reacts with this reacts with this, and then this final one, this and this, react with each other. Are all of the H plus ions which you added externally into the buffer solution, are all of these eliminated? Yes, they are eliminated. If they are eliminated, if they're destroyed, can they now have an effect on the pH of the buffer solution? No, right? Because they're not existing. If something doesn't exist, it can't have an effect. Okay, this is example one. Let's say I have another buffer solution which has five ions that act as a base. Right? They're responsible for reacting with the protons or with the H plus ions when I add them. But let's say this time I add 7H plus ions. So this is 1, 2, 3, 4, 5, 6, 7. So this H plus ions pairs with this combines with this one, this combines with this one, this combines with this, and this combines with this. Do I have two unreacted protons left? Yes. What were they supposed to react with? The basic part of this buffer. But are there any basic parts or any molecules left in this buffer that act as a base? No. So what's going to happen? These H plus ions are going to be left unreacted. If they are going to be left unreacted, then these are going to have a very, very big effect on the pH. So example, if you guys do P3, right, practical papers, have you ever seen during titration, you add a small amount of whatever that substance is in the burette, if it's a base or an acid, you add a small amount of it. And then you mix the conical flask, right? And then you add one more drop of it. And now when you shake the conical flask, the color changes. How is that possible? Adding one drop, how does that change the color? It's because if you add even one drop, that one drop might contain 8 or 10 H plus ions. And 8 or 10 H plus ions are enough to change the entire pH of the mixture, or in that case, in your experiment, the color of the mixture. So never think of it as, oh, it's only 2 H plus ions. It's not going to have any effect. No, even one H plus ion that is left unreacted has a very, very big effect on the pH of the buffer solution. So now, what do we answer here? Why was the pH not resisted by the buffer solution? It's because the person might have added so much of an acid that the buffer solution ran out of molecules that could react with this acid, meaning some of those H plus ions would have been left unreacted. Now, because they would have been left unreacted, they would have had an effect on the pH of the buffer solution, lowering the pH of the buffer solution. So let's look at the answer. See, all of the propanoate ions has been converted to an acid, meaning it has reacted. It has been neutralized, which was what we were talking about here. All of it has been neutralized, meaning H plus ions, there are still some H plus ions that are unreacted, that are in excess. So because this is in excess, these very few, even if they're very few, they still change the pH. And now this is the point when we say that a buffer solution was not successful in carrying out the job that it was supposed to do. Right. So that's the answer for this one. I know I took a lot of time for 5 marks, but this is a question which is gonna come up tons and tons and tons of times in your exams. And if you understand how buffer solution works, that's when you're gonna answer them. I feel in my first part of the explanation, some of you might not have been clear, so I just made a diagram to help understand it better. Let me know which one you found better. Yeah. All right. So yeah, that's gonna be it for today. I'll probably make a part three if some of you guys say so. But if I don't get any comments, then I would understand that that's all you guys need from my side for equilibrium. And then I'll probably shift to another topic. Again, you guys can let me know of the topic which you want topical solutions for, or do you want yearly past papers, or do you want me to explain a topic? Anything from A level chemistry, A level physics, and A level bio. So yeah, that's all from my side today, and I'll see you in the next video. Bye bye.